It's a pleasure to introduce Professor Aleksander Madry, who's a professor of computer science and specifically working on the theory of computation at EECS as well as CSAIL at MIT. And as many of you probably know, and we discussed briefly yesterday, adversarial examples have been put forward as a major cause of potential concern about the degree to which human perception and machine perception are related or not. And Professor Madry has done many important contributions to understanding and tackling with the complexities of adversarial examples. So it's a great pleasure to have him here. It's all yours then.
Okay, great. Thank you, Gabriel, and thank you for invitation. It's I am, as you probably realized by now already, I'm not a neuroscientist, so it's actually fun to be here because I discovered that a lot of things I care about, which is adversarial examples and robust ML, actually connects to neuroscience in an interesting way. So hopefully I can tell you a little bit about, like what is my view on this topic, like how we think about it, and together in the Q&A session afterwards, we can try to discover, how does the neuroscience angle look for this? So in particular, Jim DeCaro and his group already have some, papers there, and we are also talking to George McDermott, but like, I think this is really, something that, there's much more to discover there, and I would be, it would be great to learn from. Okay. So yeah, let's get started. So this will be about adversarial examples and something I will call human ML alignment. So let's talk about that. And kind of, the point of start here is, just a moment, some strange situation. Okay, the point of start here is that, of course, we have deep networks, and essentially we use these deep networks as this kind of, stepping stone towards getting synthetic human vision. Okay, and there are some reasons for believing that. So one reason is that essentially these classifiers are actually quite accurate. So if I give them an image of a pig, they tend to actually realize this is a pig pretty well. And also in general, like currently, like in computer vision, if you want to get state-of-the-art performance, you just have to use deep neural networks. There currently is no better way to do it. So there is clear, there is a clear success here. And it goes even further than this, because not only about this kind of black box performance, actually, even when you look a bit deeper, we believe that the way deep neural networks learn is kind of in some human understandable way, that there's kind of this hierarchy of features of starting with very basic ones like edge detectors. And as you go deeper into the network, they become more and more human-aligned one. So this is kind of a very desirable feature as well. And these neural networks seem to be good at cross-task generalization. It seems that like once you train a model on ImageNet, it seems to be possible to repurpose it for many other, many other like that. And also we have cool things like generative models like GANs, who allow us to kind of generate interesting distribution of images. Okay, so all of this is great, and all of this is very promising. And kind of the question that like started much of my research was just the question, okay, so everything looks great, everything looks promising. So does it mean that we are on the right path? Like essentially that all we just have to do now is just keep doing what we are doing, just scaling it up. And essentially like human vision and kind of, the performance we desire will be all the way there. And the message I want to say today is that kind of, well, despite this promising, promising signs, is actually, the answer seems to be a bit more mixed. In particular, even the best performing models seem to deviate from how human perception works in unexpected ways. And this actually has consequences that we will talk about in a moment. And as we will discover, in some ways, everything that, like the one way of trying to understand what's going on and what is going right and what is going wrong is to think about the features that our models use. Okay, so maybe, just before I already foreshadow that there might not be like, not everything is as great as we would like it in terms of deep neural networks being just stepping stone towards human vision. And in particular, like one thing that we all know by now that kind of put a dent in this view is this notion of adversarial examples. So as I said, usually if I just take a, image of a pig and run it through my classifier, it usually will realize that this is a pig, as it should. But there is a problem. So essentially, if I take this correctly classified pig And then I add to it a perturbation. It's not a random perturbation. It's a perturbation that was carefully chosen, but it's very tiny. So essentially the image that is resulting looks essentially the same to us. So we don't even see any difference as humans. What happens is that you can choose the perturbations, which are called adversarial examples, that suddenly convince this model that this is no longer a beautiful pig, it's actually an airplane. Okay, so the usual joke is that that AI is a powerful thing. It can make pigs fly, but of course this is clearly not the kind of behavior that we would expect or find desirable. And indeed, it's not only about things that happen in the laboratory. It turns out that the deep learning based vision has a lot of problems with robustness. So here is just a Tesla car on one in California that essentially wants to drive into the divider, and the driver has to take over. Similarly, this is just a bit just like a couple of months ago at the beginning of June, there is a Tesla car, which essentially there is an overturned truck on the highway, and the Tesla car in the driver assistance mode is not even noticing it and just driving into it confidently. The good news is that no one got injured in that crash, but essentially this shows that there is clearly a failure of the vision system. Okay, so these things are happening, and there are many questions that you might ask now, and essentially my research is about trying to figure out what should you do to your models to avoid situations like this. In particular, one question that essentially there are two questions that you can ask. One of them is, what do I do to avoid that? But the other question, which also captivated my mind quite a bit, was why this is a problem to begin with. So in particular, why do these adversarial examples exist? And more importantly, why they are so prevalent. So it turns out that essentially these adversarial examples are very easy to find. And the question is why? And of course, I wasn't by far the first person to ask this question. And in particular, people put together a lot of hypotheses, what could be the reason. So one hypothesis was that, well, we are working in high dimensions, so there always will be some corners that kind of fluctuate and misbehave. Other people talk about that this is just a statistical phenomenon, that essentially once you sample things, there will be some sampling noise that will be, essentially will manifest itself in the context, in the form of additional examples. Other things said that this is just, well, we are optimizing for expected performance, so the worst case performance is bad. And other things say that, oh, well, adversarial examples are just caused by the fact that, that we are using resnets, or we are using batch norm, or what have you. And essentially, all that this kind of explanation or hypothesis have in common is that they view adversarial examples as aberrations. It just says, if we did our learning in the ideal way, then essentially all of these problems would go away. And the only reason why we have these problems as examples is just because we haven't figured out yet, how to do this training properly. Okay. So in particular, from this point of view, there is this natural view of what adversarial examples are in terms of thinking about the features. And kind of what this view says is just, well, if you think about all the features that we could use to classify our inputs, well, there is a spectrum of useful features that actually help in good classification. But there is also this useless directions that model is sensitive to for no good reasons. Essentially, just because something went wrong with the model, it didn't sample all the space. There are parts, there are directions in the kind of decision space that are kind of the model is sensitive to, even though it shouldn't. And kind of the understanding was that the adversary, the way you get adversarial examples is just by playing with these useless directions. Essentially, you just add to the picture something that doesn't matter to humans, but seems to matter a lot to a model for no good reason. Okay, so essentially, the whole point is that the whole point was that if you train better models, essentially models that don't rely on the user's direction, you would avoid the sensitivity and problems from robust. Okay, so this was the view that was kind of prevalent. Actually, this was the view that we also had. But now let's try to look a little bit deeper and see if this is actually a justified view. Okay, so so the first question will be so before we even try to answer, okay, where are these adversarial examples coming from? Let's think for a moment and ask, why are adversarial perturbations bad to begin with? Okay, and essentially the point here I want to make is, so let's look at the usual, adversarial example. So we have a picture of a dog, we add to it some meaningless perturbation, and we get something that looks like a dog to us, but the model claims that this is a cat. So clearly this is undesirable, and clearly, essentially we don't like that. Like this says that something went wrong. But, and indeed, this seems that something, went wrong, but it seems so to us, humans. And kind of the point I want to make is that, the reason why this is upsetting is because to humans, this output on the right is actually not what it should be, whereas we as humans know what it should be. But now let's try to understand. So this is our human perspective. And in the human perspective, when I have this dog versus cat classification task, I know how it's supposed to be solved. Like I should use things like snout, shape of an ear. These are the features that I should use to distinguish, is it a dog or a cat in the picture? And that's how we humans solve this problem. But kind of the important realization for what I want to say today is that this is a way to solve this dog versus cat classification task, but this is not the only way to solve it. In particular, if you think about this problem from the point of view of machine learning classifiers, well, to them, this image is meaningless. Like they have no notion of image. To them, image is just a collection of numbers, like a vector of numbers. And to them, also the class dog is meaningless. Like this is just a string of characters to them. They have no concept of a dog embedded into them. So essentially, the only goal is to look at these vectors of numbers, which are images, and associate them with the strings of characters, which are the classes, and do it in a way that maximizes test accuracy. Essentially, like whenever they are asked, they get the correct answer as often as possible. That's all they care about. And kind of this is actually important because if we really want to understand this like cat versus dog classification problem from the point of view of a machine learning classifier, then you should not think about the dog versus cat, which is something we as humans have a lot of priors about. But you should actually think about something abstract, like a tap versus talk classification. What is talk? What is tap? What is talk? I have no idea. But that's exactly the point, that neither does the model know what cat or dog is, just something. And essentially, like if you look at this tap versus talk classification task, maybe if you stare at enough examples, you realize that maybe having this rectangle over here means you are a tap class, and having a rectangle over here means that you are a talk class. And kind of this is like a much better way of trying to visualize how things look from the machine learning model perspective. And now from this point of view, if you look at what adversarial examples is, well, it would look like something like this. Like when there is like, I have an example of a tap class, I add some perturbation to it, and I get a talk class. And first of all, if you look at these adversarial examples, like somehow it feels much less upsetting than the adversarial examples on the top. And in particular, at this point, if you want to say this like perturbation is meaningless, but actually like, is it really meaningless? Like honestly, everything is meaningless to us. So it's very hard to, to even judge what is meaningful and what isn't. And essentially like kind of this realization was kind of what set us off towards thinking about this question. In particular, we wanted to understand, okay, so adversarial perturbations, even though they look meaningless to us, like this kind of just black and white pixels, like they look like meaningless to us, but are they actually meaningless? Okay. And to try to understand the answer to this question, we did this, a very simple experiment. So imagine I just take a standard training set of cat versus dog. Okay, I just take it. Now what I do something strange. I will take every image of a dog and find an adversarial kind of perturbation of it that makes some model believe this is a cat. And similarly, I will take every image of a cat and perturb it in an adversarial way to make my model believe this is a dog. So now I have this new training set in which it's only adversarially perturbed dogs and adversarially perturbed cats. And what I do is I view it as a training set, but I also flip the labels. So now to me, adversarially perturbed dog in this training set is actually labeled as a cat, and adversarially perturbed cat is labeled as a dog. Okay, so in some ways we have this like clearly mislabeled training set now, because to us this is still a dog and it's labeled as a cat, and to us this is still a cat and it's labeled as a dog, but this is our new training set that we do. Now we have a training set, so what do? Well, we just train a fresh model on it. Okay, that's I have a training set, I can always train a classifier on this. And then what is the interesting thing is that what I do is I actually test this classifier, but I test it on the original test set. So I test it on the test set in which every dog is labeled as a dog and every cat is labeled as a cat. Okay, so this is the experiment. And now the question is, what will happen? Okay, so essentially, like, yeah, how will this model do on this original test set? At first, you might say, well, this is insane. Okay, so if I give this kind of new training set to a human, and let's say they don't know English, so they don't know what dog or cat means, well, the only clear hypothesis that they could come up with is that, like, you know, every dog is as a cat, and like every cat is actually labeled as a dog. So on the original test set, they would get 0% accuracy. Okay. However, you know, what is the accuracy that the model gets? Well, surprise is that it actually gets a pretty good accuracy. So for this like cat versus dogs on the CFAR10 dataset, it gets 78% of answers right. Okay, what's going on? Okay, so that's clearly not, definitely not what our intuition told us. Even of course, when we got this result first, we kind of, the first thing we did, we just checked the code if there is no flip of the label somewhere happening. It turned out that the code was correct. So what's going on? Well, this kind of, once we examine like all the assumptions we made and kind of all of the reasoning that went into this experiment, the only thing that we realized is that, well, the only thing that could be wrong in our thinking was that, you know, essentially we had this assumption that adversarial perturbations, that like the change to an image that we need to make a model believe that a dog is a cat, is something that is just an, you know, aberration, something that is meaningless. But maybe that's not the case. Maybe actually this perturbation itself is a feature, like it actually connects to actual meaningful features and predictive features in the, you know, in the model. So essentially, like what kind of the view that comes out of that is this robust, something we call robust feature model, in which if you look at this previous view of like users direction and useful features, you realize that this story is a bit more nuanced than that. And if you look at these useful features, there are, of course, what we call robust features. So these are in particular things that humans use for prediction. And these are things that are kind of remain correlated with the correct label, even after small perturbation. So things like snout or shape of an ear or the background. But, you know, so that's something that we knew existed. But also we realized that there is also this something called non-robust features. So these are actually features that are correlated with labels. So they actually are predictive, but they are very fragile. They essentially can be flipped by just small perturbation. And then, you know, to a model, when we train the model, well, it just wants to predict well. So any feature that is useful is a good feature for it. And it turns out that non-robust features actually end up being really great. They actually have a lot of predictive power about the correct answer for the input. So what happens is that, well, if the models do not differentiate and these non-robust features are useful, then that's what our models pick. And because of this preference, well, not preference, but because of doing that, because of relying on these non-robust features, that's how they become vulnerable to adversarial perturbation, because I can manipulate these features and change essentially the decision of the model based on that. Okay, so this is almost like the same as the previous view, except this direction that we are flipping using as this example, they're actually meaningful. They're not just useless directions. They actually correspond to features that are truly predictive of the correct label. So just to go back to our simple experiment, essentially what happens from the point of view is that when we created this new training set, what happened is that now the robust features are misleading. So the things that we kind of couldn't perturb, like, you know, just things that we as humans use, were now contradicting the correct label. But the non-robust features, like meaning the, you know, the effect of the flip that flipped these non-robust features to a cat position, to get, like, is now in sync with the correct label. So essentially, like, the model still is able to essentially learn this correlation for the non-robust features and rely on the non-robust features to make predictions. And this correlation, they carry over to original set and allow it to actually recognize a cat, even though technically from the human perspective, it has never seen a cat before. Okay, great. So this is kind of the change in perspective. And the question is, what now? Well, it gives us a new perspective on adversarial robustness of this kind of, this whole, you know, the whole field of like thinking about the resistance, like, you know, the, robustness to adversarial perturbations. So in particular, you know, so that's kind of that's the one conclusion. But like the way I like to think about it, it actually really gives us an insight into how our models learn. Okay, so what do I mean by that? Well, essentially, there's this kind of question of human versus ML model prior. So again, if I am a human and I think about dog versus cat prediction task, I have my prior of like what is important to being a dog. You know, it's just the snout, it's the shape of the ear, and so on and so on. However, you know, we have to understand that for ML model, they don't have this prior. Like the way they recognize that a dog is a dog might be totally different to how we, you know, humans would do it. And a priori, like solving this, you know, classification task by either way is actually perfectly valid. And there is no reason for our models to favor the human preferred version of solving this task. Okay, and indeed, like this is actually, once you realize that we look back into literature, we realize this is not a, in some ways, new finding. So people already found that the way, in particular, deep learning models succeed at different classification tasks, you know, involve relying on things or over-relying on things that humans would not rely on that much. Okay, so in some ways, we already knew that like the way models solve the classification task is not how humans would solve it. Okay. So in some ways, this is what it tells you. These are examples. Like there is nothing wrong with the models by default if they are vulnerable to these examples. The problem that we have with them is not of the problem of non-robustness, is the problem of them being non-conforming to what humans think is the kind of the right classification for a cat versus dog task. Okay, so in particular, like this realization have a bunch of important consequences. Like one of them is for interpretability. So essentially, like, you know, we would like to understand why our models make a particular decision. And what this view tells us is that, you know, non-robust features actually, well, they cannot be human interpretable, okay? Because they really, like, we as humans would never rely on them for classification. So, you know, if the model depends on them, you know, we will never understand what it's exactly doing there. So, you know, so for instance, like, you know, we can see it if you just look at the saliency maps. Like if I look at the saliency map of a like prediction, like why the model thought this is a bird, I will get things like that. And, you know, to me, it's very hard to understand like why the model is looking at all of these pixels, you know. Essentially, you know, it is solving the classification task, but it's solving it in a way that I, as a human, may never be able to fathom. So essentially, like if we want to have an interpretable model, you have to make an intervention on the training time. You have to force the model to solve, not only to just solve the task, but actually to solve it in a way that will align with how we humans want to think about the decision problem. And of course, there are methods that kind of will deliver like a post hoc nice interpretation of an image, but the problem is that they often essentially mask the actual features the models depend on. So they just like tell us a nice story of why the model might make the decision that it made, but actually this story is at least hiding part of the truth and part of the actual decision space of the model. Okay, so this also tells us that, you know, that if we want to have robust models, we really need to explicitly train them to ignore non-robust features. Okay, so there is essentially like this corresponds to something called robust training, in which essentially, you know, one way to do it, essentially you force the model, its objective, to essentially have some invariance to perturbations. Essentially, you should push the model to not make the basic prediction on things that can be easily perturbed by a small perturbation. And you can view exactly this like robust training as a prior by itself on like, you know, on how the model should learn. And you can imagine imposing even further priors that again, just align the way the model is allowed to solve the decision problem to how we as humans would solve it. Okay, and you know, once you do that, once you actually like impose this robust prior, there will be a trade-off that you will notice. Because essentially when you insist that the model is robust, so it only leverages robust features, well, then in some ways you are hampering it. Because, you know, non-robust features are useful to get good accuracy on the test set, and you are preventing the model to use them. So what you observe is that the robust models tend to have a lower standard accuracy. And also they tend to need more data to attain a given robust accuracy. So in some ways they are less efficient because again, you hamper the way they extract information from the data. And, you know, so that's kind of, that gives us view into the phenomena. And now you can wonder, okay, so, but once I impose this robustness prior, I clearly will have a robust model, but like what else will I get as a potential benefit out of it? And it turns out that, as we discovered, you get quite a lot. So in particular, what happens is what we discovered is that for the vision algorithms, using this robust prior actually leads to much better perception alignment. So essentially, like models become more human, perception aligned. So here, like imagine I have an image of a dog that correctly my model classifies as a dog, and I want to understand why. And again, the one nice way to do it is just to use saliency map. So I just look at every pixel, and I just see how much influence this pixel has on the decision, and kind of this covers the color. And if I do it for a standard model, I will get pictures like that, which kind of seem to make sense, but clearly also depend on things that we as humans would not view as important to being a dog, like this rug. So that's what you get from standard models. But if you do it to a robust model, you will get heat maps like the one on the right, which kind of seems to be much closer to how we as humans would think is the right thing to look at. Okay, and this kind of phenomena shows in many dimensions. So in particular, remember we talked about this like different levels of representation, deep representations. In particular, the second to last layer is usually viewed as the one gathering the most high level silent feature of the image. And actually, if you do it for standard models, what you can do is you can come up with two completely different images that actually end up having almost exactly the same representation, even though to a human they look different. So there are images that are essentially to a model, they look similar, but actually are quite different. And if you look at robust models, actually we were not able to succeed in finding two images that are similar in the representation, but actually are different to humans. So there's kind of this alignment of what the representation space tells us about the proximity and the human, and the human intuition. So in some ways there is kind of this alignment of representations once you use robustness. Moving on, we find that robust models have kind of better features, like meaning again, if you look at these high level features, it's much easier to assign which neuron is activated by what. So you can like find this kind of cool ways of like, oh, this neuron is detecting like insect leg, or like this neuron is detecting like frogginess. And then, once you have that, you can do feature manipulations. You can just ask, okay, can you show me the version of this image that excites the stripe neuron the most? And that's how you can put stripes on animals. Or you can do semantic interpolations, like you just take two images and you would like to have a semantic interpolation between two of them. So essentially, like, there is lots of benefits. We also recently discovered that they're actually like this robust models are actually better at transferring between tasks. So essentially, there is a lot of benefits like that. And then again, you can do more and more and more. You can look at all of the computer vision applications of deep neural nets. And it turns out that if you use a robust model, usually you will get something better, or at least something better from the point of view of human alignment. Okay, so essentially, like kind of the message that I'm trying to to signal here is that, like, in general, how deep neural networks work is really depends on choosing what features they choose to leverage to solve the classification task. And essentially, robustness can be viewed as a prior that aligns the choice of the feature to be closer to the kind of features that humans would use. Okay, so that's kind of the the high-level message of what I said, and it's general. Like I want to make just use these two slides to make this point that like kind of we really should, when we think about machine learning classification tasks, we really should think about what our model does. Like we should not just look at the accuracy alone on the test set. We should actually think about how does the model get to the accuracy it gets and why. Because sometimes we know that the way our models learn is purely correlation based, but it turns out the correlations can be weird. So just like one funny example, like one thing that we notice is that essentially like some of the ImageNet cats and also some of the ImageNet dogs, like have bow ties on them. Like essentially people put bow ties on their pets and they take pictures. And essentially now what happens is that when this bow tie is much more present in cats versus dogs, then suddenly bow tie becomes, by correlation, becomes a feature that indicates a cat. In particular, if this is the case, then if I add to a picture of a dog a bow tie, I suddenly made this, this picture look more like a cat to a model. So again, to us, this is funny. As a human, you would never think that like adding a bow tie would never change your classification from cats to dogs, but to a model, this actually would. Okay. And this is of course a funny thing. Like this is just about bow ties and cats versus dogs. Like who cares? This is just amusing. But it turns out that exactly the same phenomena show up in much more serious contexts. In particular, in the healthcare, there's a lot of talking about use of deep learning for healthcare. And essentially, people say, oh, I use this deep neural network classifier and outperforms physician at diagnosing, I don't know, just like whatever is the lung disease that I want to diagnose. Okay, let's say tuberculosis. And people like did that, and they were super happy with the result. And they said like in 5 years, essentially radiologists will be out of job because of deep learning. But then they realized that it's not as easy. Essentially, like they look a bit deeper into why these top performing models actually perform so well. And they realized that these models, for instance, like one of the models relied on the type of the X-ray image as a kind of important feature for making the prediction. And then they realized that what happened was that like tuberculosis is relatively rare in the developed countries. So to get a positive cases of tuberculosis, they have to import images from less developed worlds, and they usually have older machines. So essentially, the model never really had to even diagnose if this image has a actual tuberculosis or not. It just had to decode which machine took the image, and if it was an old one, then it's very likely this was actually a positive case. And if it was a newer one, it was a negative case. And similar thing was with with putting a ruler on the kind of a picture of some change on the skin to see whether this was a malignant thing or not. Again, when you go to a physician and they take a picture, they usually put a ruler next to it because that's a diagnostic practice. So essentially, like a presence of a ruler in the picture kind of becomes a feature that makes the model believe that this is a malignant change. Because of course, if when you go to a doctor, usually you have a good reason for going there. Okay, so in some ways, like there are these patterns, like type of the image or the presence of the ruler in the picture that are predictive, but they are also very misleading. Like these are not, like, even though the models get very good accuracy, like better than humans accuracy, they actually clearly are not solving the task we actually intend them to solve. Okay, and just of course, like you might ask yourself, like, what do I do? Like, how do I figure out if my model actually is doing something it's not supposed to? And no, in general, there's no good answer, but there is at least one cute tool that we kind of found that you can do when you use robust models. We call it like counterfactual analysis with quotes, because it's not really counterfactual, but you will see why this is the name. And essentially, like, so imagine here we have an example of an input from ImageNet that it's correctly labeled as insect, but a model, even in a robust model, claims this is a dog. And at first you might say, the model got things wrong, this happens, just let's move on, nothing to see here. But actually what robust models allow you to do is they allow you to ask, okay, if you believe that this image is a dog, can you morph this image to make it look even more like a dog to you? Okay. And when you ask this essentially model about like doing that, what you will get is the picture on the right. And if you look at this picture on the right, well, then you actually see in the top left corner, a dog. And now the prediction of a dog makes perfect sense to you. Okay. But now what is interesting, if you look at the original image and you look into this, top left corner, and you will squint your eyes, you realize that actually, like, the arrangement of the insect there kind of looks like a dog's head. And ImageNet has a lot of dogs in it, so it actually, like, whenever there is a chance that there is a dog in the image, they will go for it. So essentially, like, this is kind of the root of what made the model actually classify things the way they do. So you can do this kind of reverse engineering. So in general, like, you can view of robustness as kind of this framework from controlling what correlations we extract, what correlations the model extracts from the from the input. Okay, so that's all I wanted to do. Like, I know I went fast, so I'm happy to revisit some of these topics in a moment. So I just wanted to pontificate a bit and like say what might be the takeaways from this, what I said. So first of all, there's a question about adversarial examples, and they just say that adversarial examples arise as this, they arise mostly from non-robust features in data. Okay, they could also arise from glitches in the model, but by far, naturally, they, they arise, because of this like reliance on the non-robust feature in the data. And the point is that non-robust features are actually, they do help in generalization. So it's nothing like we should not blame the model that it uses them. Actually, if its only goal is to do good generalization, understood as just performance on the test set, they actually like should use them, and it's a good thing they use them. Okay, but then once we like allow them to use them, well, we have to be okay with these examples. And also we have to be okay with the model as being hard to interpret, because essentially if I want to have interpretability, I need to make sure that the way the model kind of solves the problem is in a way that I as a human can comprehend to begin with. Okay, so, and as I said, like this robustness prior, like training models to be robust, turns out to lead to more human aligned representations. And because of that, they enable us to like, a broad range of vision applications in a rather simple way. And also like they support finding these simple counterfactuals that I just told you about. Okay, so this is about the adversarial examples, but again, I just want to kind of reinforce this message that in the end, from the ML point of view, what you really should think about, like the lessons to take here is that it's really not like, it's really about, whenever you evaluate a model, you should not just look at the accuracy, you should actually understand how your model got to this accuracy and really know how to control, what our models learn. Because what they learn is not what what we actually think it might be. So you can ask, what is the right notion of generalization to have? Maybe the current test set generalization is just not good enough. It clearly isn't. And what features do you want our models to use? In particular, how much do you value the model being human aligned? Because making it human aligned or interpretable will come at a cost, because you are hampering the predictive power of your model. So you have to decide when this is a good thing and when this is not a good thing to do. And again, robustness is just this kind of framework for engineering, like which features your model relies on and which features it does. And kind of, again, in the spirit of the summer school, like one question I really want you to ask, and again, I'm happy to go in more detail during the Q&A session, but like essentially, like how like the thing that really interests me, and I know some partial answer here, but I think there is more to be understood here, is like essentially how this robust ML view should inform neuroscience, and also the other way around, like how neuroscience can essentially inform how we develop robust machine learning classifiers. Okay, so that's a question that I really would be curious to hear your thoughts. And there's on the website, there is more materials to do. There's in particular my student Shibani Santurkar. She did, she put a longer version of this kind of presentation online, and there's a video, and also she had like put together a lot of demos to play with this robust model. So I really encourage you to take a look there, and also like gradientscience.org. This is our research blog of our group where you can learn much more about this, about this robust ML. And now, without further ado, let's ask some, like, I'm happy to answer questions. Thank you. So yeah, okay. So essentially, like I'm now looking at the Q&A, and I guess I will just go over questions, like ordered by like how much they are upvoted. So we start with a question by Miguel. And what he asked is, many of the adversarial attacks are done at the pixel level, but we as humans don't analyze image content at that level. How we can compare between artificial and the biological systems, taking that information into account? So that's a great question, and in some ways, something that exactly is, one of the things that I think this connection to neuroscience would be extremely important for robust ML, is that yes, like to me, this kind of view on pixel level perturbation is it's a good sandbox for understanding the tools and the phenomenon, but this is not the kind of perturbations you should think about. So in the way, again, in the end, it's all about representations. And when we talk about biological systems, and actually, like, well, we know that biological systems have certain representation in our brain, like the way they perceive the world is, they just use certain features, they pay attention to certain signals. And what would be great is to actually replicate, if you want to have human-like AI systems, is to figure out how to replicate, these representations that humans, for instance, use, in our AI models. So in some ways, the dream I have is that, like, in some ways, robust training, as we said implicitly, seems to push the models towards, being not sensitive to pixel-wise perturbations and not sensitive to the things that would not make sense to humans, but we are still a long way away from that. So kind of like, what I think would be interesting is understanding what kind of prior / what kind of representations we can extract from our knowledge, how biological systems, biological vision works, to replicate it directly in our AI systems to make them more robust. Yes, so it has just this follow-up question. Like, it connects to autoencoder, but I just don't want to go into that. So I just want to move to the next question. But like, yes, it connects to autoencoders. Again, in the end, it's always about how do we represent and process the visual data we get. Okay, the next question is from Ferdinando. Do we know if those failure of self-driving cars are due to adversarial situation? That's a great question, and we don't. And in a sense, this is the scary part, but we don't even know why these things happen, because again, this is Tesla. This is Tesla's, this is Tesla's internal things, internal knowledge, and they don't share. So we don't know. Like definitely, it seems, at least in the overturned track, it seems that this was like out of distribution input, but maybe it just like have never seen, like overturned tracks, so just it panicked and didn't know what to do. There was also the unfortunately tragic Uber crash, like many months ago. And then there was actually an audit and analysis of what happened. Essentially, what happened there was that the model was very brittle, like it was changing the prediction of what is in front of it. And the system essentially, like whenever each time the model changed prediction, it kind of delayed making a decision, which was again like a mistake of the model. And there it's like, it is clearly can be connected to a brittleness. It's not clear this is like adversarial brittleness. I view adversarial example as an extreme manifestation of this, of this like standard brittleness. But yes, but there I would claim that exactly this is the brittleness, which was at least partially at fault. And also there was a bad systems engineering in terms of safety, but the root cause was adversarial examples. Okay, now Sreya, there is a question by Sreya. So my question is for Dr. Madry from his reading list on robust features for adversarial examples. Usually, for neural networks, the priors used for training is provided by the dataset, initialization of hyperparameters. What are the other priors that can be introduced while training? Also, how do we differentiate between robust and non-robust features? If we make our models less sensitive, how would that affect generalization transfer learning? So that's a great questions. And, I guess you asked them, before like I go to this part of the talk, but like essentially like, yes, so let's go one after the other. So yeah, so how do we impose the priors beyond dataset and the hyperparameter choice? So I already like gave one, is this robust training. Again, I didn't tell you how you do it, but essentially you during the training, you essentially like figure out, how to trick the model. Like you present it with an input and you figure out what perturbation of this input would make the model misclassify. And then essentially you present this misclassified input and you tell the model, okay, you should not have been fooled by this. And essentially what really happens is that you are essentially forcing the model to be invariant to certain perturbation. This is actually a prior. This is the robust prior I'm talking about. So you can induce it during training. And again, in the reading list, like some of the blog posts like go in depth on how it works, and I encourage you to look there. Now, how do you differentiate between robust and robust features? Like this is kind of part of the Sphinx. This is kind of this weirdness here, is that like essentially what we are saying is we're just saying, well, I don't know how to differentiate between the robust and the robust features. All I'm just doing is I'm making sure that your decisions is invariant to small perturbations. So what it ensures is that you will not rely on non-robust features. So then the only features left that you can rely on are the robust one by definition. But so kind of implicitly we ensure that you are not using the non-robust features, but we don't even have a like we can't essentially look at the feature and say, is it robust or non-robust? So it's always kind of very indirect way of dealing with that. And yeah, as I said in the talk, like yes, we are making models less sensitive to actual signaling data, and this has consequences. So it definitely affects generalization. The accuracy of these models gets lower. Again, you might ask, is it the right generalization to measure? Because like, if you did it because of some weird signal, like predictive signals, but not human aligned signals, like, is it the accuracy you actually would like to measure? So in particular on ImageNet, the state-of-the-art classifiers like seem to outperform humans, but maybe they outperform them because of the cheating. Like in some ways, they use signals that are predictive of, of the correct label, but actually might not be what humans would deem like the correct way of doing the classification. So we have actually a recent paper, you can find on our blog, essentially that kind of goes exactly in this issue. So I will not go any further, but it's a good question of like what really like the right notion translation should be. But yes, if you just look at the accuracy in the test set, you pay for this when you do the robust model. Interestingly, from transfer learning, as we discovered, even though we know that the better accuracy helps you with transfer learning, it turns out that even despite of getting penalty in accuracy, robust models still tend to outperform standard models in transfer learning. So this is the new result that we had. It's also on the blog. On the blog, and so there it seems that the benefits of the robust training outweighed the penalty of having lower accuracy. Okay, the next question is by Quadra. So the overparameterization and depth of neural network essentially is what lends them the power to learn exponential complex nonlinear functions. But the overparameterization is also at the same time giving 1 million knobs to manipulate the network as per one's will. What do you think is the fundamental problem here? Is it the overparameterization or the learning algorithm, or we need better regularization methods, or do we need some fundamental change in the structure and the mathematics of neural networks? Well, that's a big, I would say, even like $1 million question, or probably actually $1 billion question at this point, given how much money is in kind of figuring out how to make networks work better and more robustly. So like, yeah, so this overparameterization, like it seems to be a feature, not a bug of deep neural. Okay, so what is amazing about deep neural networks is that they are extremely good at finding good features. Like somehow they look at the input and they latch on like to some features that are useful to get good accuracy on the training set. So we don't really understand this mechanism yet. Like we seem to believe we have evidence that overparameterization helps us. This infinite flexibility of networks is what kind of makes it easier for them to figure out the right features to use. But on the other hand, the problem is that, like as we saw in this talk, is that sometimes the things that they learn to get good, like accuracy in the test set, are not the things that we actually would necessarily want them to learn. So what we need to figure out is exactly like figure out this, some ways of imposing the priors into the model, and ideally we would like to impose the prior while keeping the benefits of this. So again, I don't know what is the answer here. That's that's a very active area of research, but like we view like this robust training as one way of imposing the prior that kind of respects the network's overparameterization, although it seems to be restricting it. So I guess it's going a bit counter to that, and kind of we are finding at least some some trade-off between flexibility and extracting all the features that allow it to get good accuracy on the test set versus consideration of being human aligned and robust. But like honestly, I'm not able to say anything more than that because it's a fascinating problem. I just don't know. Like I will not, especially on record, I will not say any speculation of what I think is the right way to go. Okay. Okay, now Kwan asks, there is some work from Google Brain that showed when humans are presented with still examples very briefly, i.e. simulating only a feed-forward pass of visual sign like in CNN, they make similar errors as CNNs. How would we make of that? Yes, so that's a very interesting paper. Yeah, I like it a lot. And essentially like this goes back to the question of priors. Like in some ways, again, like I am not a neuroscientist, so I cannot fully like judge, but I think some of the people on the paper actually are neuroscientists, so I presume they did the experiment right, and it's really like only giving enough time for like the forward pass, but not for the backward pass. But like I think this actually illustrates exactly the point that we are making here, is that somehow the reason why we as humans tend to be robust to adversarial examples, might be that because we have understanding of the world, the physical world around that, and maybe this understanding is what kind of corrects for us to not depend on things that we know is not important, and this like the nature told us that is not important. So, what is interesting thing here is that like, it might suggest that like our visual system still perceives this kind of small differences. Like, yeah, so essentially like, okay, so the part that I definitely, I feel definitely is in line with what we found is that, once you engage the human priors, this kind of make you robust to the examples. And I just kind of didn't, like I'm still on the fence, understanding how to interpret this fact that actually humans seem to be equally, like equally or comparably, comparably sensitive to this thing. So kind of this is not incompatible with our theory, but I still don't kind of, I'm not sure if I think this, like what to think of that. So kind of, yeah, it's maybe not a very satisfactory answer, but like this is what but I find this paper very interesting. And I actually would love to have more experiments like that go in depth, like in some ways just to reproduce this, this experiment and kind of, do some kind of, creative extensions of that. So if some of you do something like this, please send me the paper. I would be very curious to see this. Okay. Now a question by Sophie. Regarding your final question, how much have people tried to understand the biological reasoning behind optical illusions and how they relate to the underlying causes of these adversarial examples? So that's an excellent question, because again, in some ways, like this is exactly the point that I like to make, that essentially, that humans also seem to have adversarial examples. They are very different to adversarial examples that, the standard neural networks seem to have, but they're called illusions. So yes, that would be very interesting thing to do, is just kind of to understand exactly like, why illusions work, like, and honestly, I'm sure people studied this. I probably don't know what is the right literature. So if some of you know the literature on trying to, like, from the neuroscience perspective, analyzing why certain illusions, like optical illusions, work or don't, like, please do send it my way. But yeah, like I just view it as a evidence that the magical, like the optical illusion is evidence that humans also have their blind spot, like essentially like the way the representations they use, they also kind of depend on things that are not robust features, but of course the robust feature here means something different. And yeah, it would be fascinating to compare what is the mechanism, like we kind of understand what is the mechanism for this for neural networks, and then understanding, what is the mechanism for humans, like again, hopefully someone already figured this out. I would love to know. So yes, if anyone has any leads on that, just please send me an email. Okay. And now another question from Sophie. So for medical diagnostic purposes from images, is it known whether models that are robust to human perception are better or worse than one that include non-robust features to diagnose illness? So that's an excellent question. So that kind of goes back into saying, okay, clearly things that are, more human-like and, essentially like if the model uses only things that I as a human, use, you might argue that like, yeah, this is the only things I should be using. And again, in some ways, like what you are getting there is like hope of interpretability and explainability. So that's kind of, that's clearly, giving you some confidence and good feeling. On the other hand, sometimes there might be actual signals, like legitimate signals that we as humans can have, but the model is good. And essentially, like, so you could imagine that you could have a diagnostic device that uses some things that humans don't perceive, and this actually makes it a better and in some ways more robust, like diagnosis tool. So for instance, like I know that apparently like dogs can, I think they can do diagnosis of some kind of cancer because apparently the way, patients smell changes and they can actually detect it. So you wouldn't tell the dog, no, you're not allowed to use your smell because we as humans, we don't have such a sensitive smell. So in some ways, like, so clearly there are moments where using non-robust, like things that people might, that people may not perceive, like this actually might lead to, this may be actually desirable. But again, like, so, so essentially this is what makes this tricky. Like you need to negotiate this trade-off between, okay, is the model using things I understand and I can kind of ascertain are legitimate features to use versus let it use things that, might be useful and legitimate, but might be also not legitimate. So of course, like when you talk about non-robust features, you have to really, also define what really non-robust to what. Like, so if it is like pixel-wise perturbation, you might say, oh, in my pipeline, we control very well for, for a kind of essentially like, I don't expect the the pixel-wise patterns to change, and maybe like this, like you will not this will not lead to the brittleness that you will be worried about. But maybe there are particular part of perturbations that happen naturally that if your model is non-robust to that, that might be a problem. So there is no clean-cut answer here. Yes, of course, like doing things robust to everything would, like, on one hand, it would be a safe choice, but clearly this way you will diminish, like the only absolutely robust classifier is the one that is a constant classifier, right? So clearly you have to find, find some trade-off here. And this will be something that actually, you need to figure out on the case-by-case basis. And I do believe that healthcare is a particularly important field to exactly, do this kind of explorations. Yeah, and I see that Danish essentially made the point that I just made about that. Sometimes you might want your your diagnostic tool to essentially use things that are not accessible to you. Okay, now Laha has a question. So how can we create adversarial examples close to real-world samples? Can we build an architecture like GANs to address this issue? One network is to add perturbation, the other one does classification. So in some ways, this is an interesting question. In particular, the interesting question is like, how do we kind of capture the richness of potential perturbations that you might worry about in the real world? Because yes, in this talk, again, I wasn't too explicit about this, but in this talk, we look at small L2 pixel-wise perturbations, which is clearly a nice point of start and a sanity check. But in the real world, you might have things like rotation of an object. You clearly would not expect that small rotation of the object should change classification. You can think of some blur, of fog, like all this, like other kind of perturbations that will not be just captured by like small pixel-wise perturbations. Like, how do you capture all of that? And the answer is that we don't know. Like, this is kind of, again, something that we need still to think about. And maybe some guidance from neuroscience could be useful here. Like, for instance, like for hearing, we know what is the, like how the ear is built, and we can kind of try to, formalize what kind of signals the ear will distinguish, perturbations the ear is sensitive to and what it is not. But yeah, so this is the big question. You could, like in particular GANs, like people like to believe that GANs learn whatever you want them to learn. I think the answer is a bit more nuanced than that. There are like significant problems with this, but in some ways, I think there is a connection between GANs and robust training. Like in some ways, robust training to me is kind of more principled way of trying to implement the ideas, the core ideas behind GANs. And indeed, like I just flashed the slide in my talk about this, but essentially you can use robust models to get generative models out of that fairly easily and in some much more stable way than GANs do. But yeah, but like this is just like, like essentially like still like this is an open question. And again, I think this is something exactly at the intersection of neuroscience and machine learning. Okay, so now there is a question from anonymous attendee. How do you quantitatively differentiate between the robust and non-robust feature? Is this acquired from human ratings or something? No, so as I said, like this is kind of this subtle thing that essentially like we never rate what is like robust versus non-robust. We just essentially make the training, encourage the model to be invariant to certain types of perturbation. So this way, essentially, like, what happens automatically, but in not a fully controlled way, is that any signal that like is, too sensitive to particular perturbation will essentially be always weeded out. Like you will not let the model to rely on this. But of course, you can imagine there can be signal who is kind of just around the threshold, and maybe it has some influence that is diminished or kind of partial. If only on some subpopulations, it actually is active, on some subpopulations isn't. But yeah, we don't have any explicit way of trying to quantify that, unfortunately. So, again, anonymous attendee. So in the peak airplane classification example you gave, couldn't the problem be related to the fact that we humans watch the image for some time with slight variations, perturbations, and the model only looks once? So yes, this kind of touches exactly like on this, like, Google Brain paper that was mentioned before about like how much of our robustness comes from our like, I would say common sense understanding of the world. And I do think that it definitely matters, maybe not for the, like, I don't think it really matters for the, like again, this is still to be resolved, but I don't think this matters that much for like tiny pixel-wise perturbations. But I think for this, more complex perturbations, it definitely matters, right? Like again, if I rotate things, like recognizing that slightly rotated dog is still a dog, it's not actually a priori clear to you. Yes, like you have to know what the dog is. You have to, so you have to kind of, your brain has to tell you what the dog is, what makes a dog be a dog to actually be robust to it. So I don't think actually, this force on time plays a role in this particular example, but I think it is a big ingredient of robustness of a human visual system. And in particular, like the thing that you said, that we actually see the object, essentially in, like whenever we see the object, we see it with different, we have two eyes, and we have kind of, we are essentially moving our eyes a little bit. So essentially, like we see this kind of a bit different, different cast of the project, of the object, is definitely helpful. Although again, you could simulate, if you have a just 2D image, you can say that this is kind of, this effect is, it's not really relevant. But yes, I think in general, it definitely is a big part of what makes our humans more robust to the, to the perturbations we want to be robust. Okay, so yeah, I think I'm out of time. So sorry for like not answering to all of the questions, and yeah, thank you for asking all these questions.
Thank you very much. That was a great talk. Thank you.
Thank you.